Okay, so the plan for today is to finish up section 3.2, the product and quotient rules, just a couple more examples from that section. Work through 3.3 derivatives of trig functions, and we should have time today to start 3.4, the chain rule. Um, I shared in chat a practice worksheet for chain rule, um, and I'd recommend kind of working through that on your own. It's not, to be graded or for anything related to the course grade or anything like that, but mainly just for practice. And we'll probably start off the next class meeting with reviewing that. That's of course presuming we do get through the chain rule. I think we should get to the chain rule and get through an example or two, and then you can work through that practice worksheet. So one quick note about the chain rule is, um, I think a lot of courses have kind of like almost like a hump day kind of topic that it's like, okay, you come up to a certain topic in the course and it's kind of the make it or break it for the course. Like in algebra, it's factoring. It's kind of like stuff leading up to factoring, people tend to get pretty well, and it's not too big of a learning curve. But, in Math 90, they hit factoring and it's like, okay, if you put in the time, if you put in the effort, you drill the problems, you get really good at it. If you're really good at factoring, the rest of 090 is, going to be not easy for those folks, but, manageable. But if you don't get factoring, it's like, it's probably going to come up on every other problem or nearly every problem from that point on. And the rest of the course is just not going to work out. The chain rule is kind of like that in Calc 1. Um, so I think the chain rule is kind of that like make it or break it section. It's sufficiently complicated that it's not really easy. I mean, the applying the product rule is, pretty straightforward. Once you do 3 or 4 problems, you're like, okay, I get how to do this. The chain rule, not quite so much. It's complex enough um, that applying the rule properly from the calculus standpoint takes some work, but also the pre-calculus and the algebra concepts that you need uh, to understand how to apply the calculus concept properly is also somewhat demanding. So that's why the plan ideally is that we're going to introduce the chain rule today, maybe work through a problem or two, that you'll work through several problems on your own on this practice worksheet that I posted in the chat. I also posted on Blackboard just to, in case you lose track of it or something. And then when we come back next time, we'll hit the chain rule again. So I like this, for these more difficult concepts, hitting it in 2 consecutive class periods. So we're going to try to do that. Hopefully I'll make it through things quickly enough that we get at least a small start in the chain rule today. But I would definitely recommend, this is the kind of section where, um, taking 2 or 3 problems a day and doing 2 or 3 problems a day every day for the next week or so, you'll get, 20, 25 problems under your belt, and it's going to feel a lot more comfortable at the end of that. If you try to do one of these things where like you wait until, 10 o'clock at night on a Sunday night and try to blast through them all, um, number one, that's just kind of stressful and you might not get a good score on that homework. And number two, that's not a really great way to learn it. So try to do, a couple problems a day, every day for the next, week or so related to the chain rule. Just pick a couple problems out of the book, or you could even just make up a function and try to differentiate it. And then, go to an online calculator or something, see if the answer that you got is the correct answer. Um, so that is my little spiel on the chain rule. The quote of the day for today is that difficulty tends to increase non-linearly with complexity. So the idea here is, especially relevant to math, I think also relevant to life, but if we're looking at solving a math problem in this way, and we start out with a certain amount of complexity, an easy to think of example is, for instance, solving a linear equation. If we have a linear equation where both sides of the equal sign, we have some parentheses going on, some exponents, lots of different, exponents on numbers and so on. We could try to start applying equation solving steps, but that increases the complexity and makes things messier. And then we're at the top of this complexity mountain, we have to work our way down the other side. That's going to be quite difficult, right? If things get, say like twice as complex, they probably get much more than twice as difficult to manage. I'd much rather simplify first, as simple as I can get it, then do one equation solving step. That tends to make things a little messier, a little less nice looking, and then simplify as much as I can again, right? I'd much rather take this trajectory because each of these simplifications is going to be much easier, much less error prone, much less difficult to find the strategy, um, than trying to, see this whole strategy all at once to decrease the complexity from something very complex to a simplified form. And I think this applies to life as well, right? One example, about a year ago, my sister and her family moved from Ireland. She was living in Ireland for about 5 years. The guy that she married is Irish, so they lived over there for a while, moved back here, and that's obviously an incredibly complex situation, right? You're moving kids, you're like moving your whole lifestyle to a different country. There's visa things and all that kind of stuff to deal with, and um, so kind of the more that you can manage that complexity in an already complex system, like the more things you can take off the table that you don't have to manage, um, the better. So, so I think that applies more broadly than in math, but definitely applies in math. Okay, so the product and quotient rules just recall that the derivative of the product, essentially what we do is we write the product twice, f times g added together, and then in each term we differentiate one function or the other. And this does generalize the derivative of the product of a bunch of functions. We write that product of a bunch of functions that number of times, and we differentiate a different function in each term. And the quotient rule, the derivative of the quotient, we have derivative of what I'll call top over bottom. So we have bottom derivative of top minus top derivative of bottom, if I can select that, top derivative of bottom over bottom squared. This is one of those things you can maybe like kind of remember it with that mnemonic. That's how I do it. I have to say it from start to finish every time, or I'll get it wrong. Or after we talk about the chain rule, we can reinterpret this as the derivative of the product of f of x with g of x to the minus 1 power. And that's another way that we can kind of avoid the quotient rule, and it can be quicker in some cases. Okay, so our first example today is actually Dennis emailed me and kind of asked an interesting question, and I probably should have emailed you back and said I'll cover that in class, but I realized just before class, I'm like, oh, I never actually emailed you back, but I wanted to actually talk about this in class because it was a good observation. So he said, I noticed that last time we did e to the power x plus 1, the derivative of that was e to the power x plus 1. We know that the derivative of e to the x is e to the x. That was the theorem. And we actually saw that the derivative of e to the 2x was 2e to the 2x. And his question was basically, does this idea generalize to an arbitrary e to a linear function? Is f prime, well, the coefficient of x is m, and it seems like that coefficient kind of comes down, and it seems like the constant term just sticks around. Is that true? We can kind of argue in a couple of cases that it is, right? We can say, well, e to the mx plus b is just e to the mx times e to the b. So I noticed that this is really just a constant. So it's going to come out of the derivative. We take the derivative, it's going to come back in and kind of glob back on to the exponent as a plus b. So yeah, that part, that plus b part, we would certainly expect to be there. So this is an important idea in math, is we see some examples, we might recognize a pattern. Pattern recognition is a really big deal in math, recognizing that, oh, these examples all kind of fit a certain pattern, e to a linear function, mx plus b. These are just different instances of that. can I maybe come up with a generalization, an abstraction? Can I say, I've looked at these particular eta linear functions and seen what the answer was. Can I generalize away from that and say, what's the answer for e to any linear function, and use that idea, maybe bringing it back to the surface to solve the derivative e to the linear function for a different problem? Or maybe can I use that idea as a jumping off point to another idea, right? But once we recognize a pattern, we want to investigate a little more thoroughly. So I think this is a pattern that seems to work for these. Is it just a coincidence? Does it work in general? The spoiler is, yes, it does work in general. This is a general rule, and we'll actually be able to prove this carefully with the chain rule in a minute here. But I wanted to show that even with the product rule, we can prove kind of a smaller version of this. So let's suppose that m is a natural number. Let's just take that special case, right? Sometimes we have difficulty going to the full general case, but maybe we can take a step along the way and get close, or maybe we try to take a small step and we realize, without doing a lot of work that, oh, okay, it fails this smaller step. It's certainly not going to apply in the general case. That could be another result. So if m is a natural number, then e to the mx is e to the x plus x, and etc. m times, but that's just e to the x times e to the x m times. And therefore the derivative, well, what would I do? I would take this product, right, by my generalized product rule. This is why I wanted to do this in class, because it's just a nice application of this generalized product rule. I have this product. I write it m times. So I write, well, I'm not going to write it up, but I write the product once and then again a whole bunch of times. In the first one, I differentiate the first e to the x. But wait, that just differentiates to the same thing, e to the x. In the second one, I differentiate the second e to the x, but that differentiates to the same thing, and so on. So actually, all of my copies where I've differentiated the first factor, the second, or the third, they all match each other and they all match the original copy. I just have m copies of e to the x multiplied by itself m times. Right? When I differentiate the first function, e to the x, it just stays the same. When I differentiate the second function, e to the x stays the same. So all of these copies are just actually the same as the original product. So I have m times that original product, which is m e to the mx. And that combined with the understanding of what happens to the constant bit, we have verified, we have really proven that this is true, but in the special case of m being a natural number. If m is like 3.5, or if m is like -2, I can't really do this, right? I can't kind of split it up this way and use my product rule. So for more general m, well, I would need something more powerful for that. And when we get to the chain rule, we'll actually see that we can apply the chain rule and get this for all real m. So coming up in section 4, we will be able to solve this for all real m, and I will leave that as an exercise after we get to chain rule. There we go. Yeah, but I thought that was a really good insight and a good question, and so I figured I would just kind of address it here, and it's a little easier to address it like this than writing all this out in an email or something. But that kind of warms us up for product and quotient rule. So a couple more problems here, and then we're going to jump into 3.3. So here we have a function h of x equals 1 over x plus e to the x. And we want to compute its derivative h of x. Now, again, I could think of h of x as x plus e to the x to the negative 1 power, and then apply the chain rule. So if you're going through your notes, we're going to work this out using the quotient rule. But if you're going through your notes after we cover the chain rule, you want a little extra practice on the chain rule, work this problem, work this problem, you know what the answer should be. So you should be able um, to check and make sure you get the right answer. So a little extra drilling on the chain rule, never a bad thing. If you're going back through your notes, hit these two problems with the chain rule once we get to that topic. But for over here, I see that h of x equals f of x over g of x, where f of x is just the constant function 1, and g of x is x plus e to the x. H prime of x is what? It's that whole messy numerator over the original denominator squared. So let me just start with that. So I have an over g of x squared. I like to write that first because I feel like doing all the derivatives and the minuses and stuff up top, it's easy to do all that complicated stuff up top and either just flat out forget the denominator. I don't think that would happen too often, but I find that it's actually really easy to forget that the denominator is squared. I kind of feel like, every person has their own little idiosyncrasies, things they tend to forget. And that's one of the things that I've recognized that sometimes I make a mistake on. Since I recognize that, I kind of am proactive about that. And I put that a little earlier in the order of operations, so to speak, not in the literal order of operations, but in my way I do my derivatives here, just so that I don't mess it up. And you might notice that too. You might, in a certain area, notice, I tend to make this goofy mistake. Maybe you tend to leave off initial minus signs or something like that, right? And you copy it down and maybe you just tend to lose those minus signs. Well, you can choose instead when you say, oh, I have a leading minus sign, I'll write it as 1 minus x equals 3. Like you're going to be less likely to forget that minus sign, right? So you can, if you recognize that something is error prone for you, I try to point out things that I think are error prone for lots of people, but if there's something that you recognize as error prone for you, find a workaround for that. Find a way to make it less error prone. Okay, so I have my over the bottom squared. And what does my quotient rule say? Well, it says I need bottom derivative of top. So bottom times the derivative of the top, d by dx of the constant function 1, minus top. Well, that's just my constant function 1, derivative of the initial bottom, x plus e to the x. Okay. Well, the derivative of a constant function is just 0. So this entire first term is 0. I have a minus. The derivative of the sum is the sum of the derivatives. The derivative of x to the first power is just 1. And the derivative of e to the x is e to the x. And I think this is about the best we can do. I don't think we can really get it any simpler than this. That kind of 1 in the numerator just messes things up just enough that we can't really divide anything out. So even though the quotient rule is kind of a big messy formula, applying it, practically speaking, isn't that hard because um, you just go piece by piece. It's really keeping straight, what's the first term, what's the second term in the numerator, because if you get them backwards, then your answer is going to be off by a negative sign. Okay, second example here, we have r of x equals this rational expression, x minus x cubed plus x to the fifth, all divided by 1 minus x squared plus 2x to the fourth. We want to compute r prime of 1. Now, our standard strategy would be, find r prime of x as a function of x, and then plug in 1. R prime of x is going to be kind of messy though. But I know what R prime of x is going to be if I call this numerator f of x and the denominator g of x. I know R prime of x is going to be, I have an over g of x squared. I have bottom derivative of top. G of x f prime of x minus top derivative of bottom. And I actually know what R prime of 1 is going to be in terms of f, g, f prime, and g prime. And this is where that kind of idea of difficulty increases nonlinearly with complexity comes into play. I could I could go and figure out what R prime of x is. I'd have all kinds of x's to different powers being added and subtracted and multiplied and all of that. I could do that, and then I could plug in x equals 1 and see what I get at the end. But I could come off to the side and say, well, all that I really need, nobody asked for R prime of x. I was going to make that an intermediate solution or an intermediate part of the solution and then try to work my way back down the other side. Can I take a couple of smaller steps to get to the same place and save myself that bunch of hassle? In other words, can I find the numbers g of 1, f of 1, g prime of 1, f prime of 1, and then just plug them in here, and then I just have a bunch of numbers multiplied and added and divided? That's not nearly as bad. And yeah, I could do that. There's nothing wrong with doing that. Now, if the, you know, question prompt said, find R prime of x, part A, and then part B, evaluated at 1, well, then you need to find R prime of x. So if we needed the function for some reason, we'd need to find the function, but we weren't asked for it here. We're just asked for the value of the function at this point. So let's find f of 1. Well, f of 1 isn't bad. It's 1 minus 1 cubed plus 1 to the 5th, or 1 minus 1 plus 1 is just 1. What's g of 1? 1 minus 1 squared plus 2, or 1 minus 1 is 0, and then plus 2 is 2. Okay, now I need to find f prime of 1 and g prime of 1. Well, here I am going to find f prime of x and then evaluate it at 1. There's not really an easy way to go to get around this. I mean, I suppose I could go all the way back to the definition of the derivative, but I think that's going to be much more messy than doing it this way, right? F prime of x, 1 minus 3x squared plus 5x to the 4th, the derivative of the numerator. And f prime of 1 is 1 minus 3 plus 5 is 3. And lastly, g prime of x. Same thing here. We differentiate the denominator by itself. That's 0 minus 2x, and then plus 8x cubed. And g prime of 1 is negative 2 plus 8 is 6. And now I just come over here and plug in the numbers, not these huge, not all of these different polynomials that would multiply to be huge polynomials. What's g of 1? It's the number 2. What's f prime of 1? It's the number 3. Minus f of 1, 1, times g prime of 1, 6, over the square of g of 1. Or this is 6 minus 6 over 4, or it turns out to be 0. Actually, I have a horizontal tangent at x equals 1 here. Right, so I was much happier to increase complexity a bit and then decrease it right away for getting f prime, and the same for g prime. And here I increase complexity a bit, but I immediately decrease it, right? I mean, I have this big messy expression, but instead of having to deal with bunches of variables and polynomials being plugged into that expression, I can just deal with numbers. I can leverage the fact that I'm only being asked for the derivative of a number here. I don't need to find the derivative as a general function for this problem. Any questions on product or quotient rule, anything in this section? Okay, so let's take a look at derivatives of trig functions. So a little bit of an introduction. Let's try to compute the derivative of sine theta from the definition of the derivative. We have a theorem, a little spoiler alert here, but derivative of sine theta is going to be cos theta. Let's, I guess let's first see if that makes sense. Then let's try to prove it with the definition of the derivative. And then let's go from there. So if I have a function sine theta, so this is pi, and this is 2 pi. This is sine theta. And if I look at the function cos theta, I'm trying to draw this pretty reasonably accurately. If I imagine what my slopes of my tangent lines for sine theta look like, well, I see that I have a couple different horizontal tangents of sine, and they correspond, oh, and this is cos theta. They correspond with the 0 values of cos theta. So the slopes, the horizontal slopes, the slope 0 points of sine theta are the values of theta where cos theta equals 0. I noticed that sine theta is going to have negative slopes for its tangent lines. Its slopes are going to be slopes of its tangent lines are going to be negative between those two horizontal tangents, and I actually see that cosine has a negative value between those two zeros. I see that sine has a positive slopes for its tangent lines to the left of pi over 2. Cosine evaluates to a positive number in that area. And similarly to the right of 3 pi over 2, the tangent lines of sine have positive slope, and cosine evaluates to positive there as well, going up to 2 pi. So I can argue that it's at least plausible that this relationship could exist just by looking at the graphs. I might have even been able to guess this relationship if I kind of looked carefully at the graphs and put in, you know, 0 here and here. Maybe I did a couple cycles. I know that because sine is cyclic, its derivative should be cyclic as well, right? And maybe I could have put pieces together and maybe even made an educated guess that the derivative would look maybe like cosine theta. Okay, now that I have this idea, let me see if I can prove it. So let's come over here and look at the derivative of sine theta. So by definition, what is it? It's the limit. Since we're in geometry here, instead of using h, I'm going to use delta theta. You can write h if you prefer, but it's just, I don't know, it's, you know, a little more usual to see in the geometric context, like delta, you know, independent variable or delta dependent variable. But we want limit delta theta goes to 0 of what? Of, well, delta y over delta x basically, or this is sine theta plus delta theta minus sine theta over delta theta. Okay. Delta theta is like one thing. It's like H, like H, basically. So delta theta isn't like two things multiplied together. It's just the change in theta, change in angle. Okay, so what do I want to do here? I don't think doing like an add and subtract the same thing is going to help maybe a ton here. But I want to look at my sine of the sum of two angles. I actually have a formula for this. Um, So sine of the sum of two angles ends up being, I'll show you how I figure it out. So sine of A plus B. Well, I know two things. I know that sine of 2x equals 2 sine x cos x. And this is, of course, sine of x plus x. So I know that sine kind of mixes the trig functions when I have the sine of sum of two angles. So I'm going to have sine something cos something, and then another sine something cos something. Because that's how, if I put x and x in here, I get sine x cos x plus sine x cos x, and that gives me a 2 sine x cos x. I also know they have to be added together. So the sine of sum of two angles, it's going to keep the sine, and it's going to mix the functions. Okay. And then, of course, I have a and b switch which function that they're in from one term to the next. So I actually don't remember these sine or cosine of sum of two angles formulas or difference of two angles. I don't remember the formulas because there's just a lot of ways to get them mixed up, right? Some of them have minuses and you got to get the right thing first and second. But I remember my double angle formulas and I remember generally kind of how these work. So what do I have over here then from that? Limit delta theta goes to 0 of, I know I have sine of theta cosine delta theta plus sine delta theta cos theta minus sine theta all over delta theta. Now, each of my terms in the numerator has a factor that only has theta in it. So like a sine theta or a cos theta. If I kind of cordon those off, what do I end up with? Well, I can factor a sine theta out, and then I'm left with cos delta theta minus 1 over delta theta. And then I can factor a cos theta out, and I have sine delta theta over delta theta. So really what my problem comes down to is evaluating these two limits. I noticed that both of these are indeterminate forms. As delta theta goes to 0, I end up with something that looks like cos of 0, which is 1, minus 1, 0 over 0. Or as delta theta goes to 0, I get sine 0 over 0 or 0 over 0 again. And it turns out I can't really make much headway here. The way that the book approaches this, I think, is they directly attack these two limits with a geometric argument. In my mind, it's, I mean, I can follow the steps of the argument and it makes sense, but it doesn't seem to me to be super intuitive. It's a perfectly fine way to do the proof. Maybe even in some senses a better way to do the proof. But I think it's less intuitive. So we're gonna kind of pause here. We did get this, and this is going to be beneficial in the future. So we didn't waste our time here. I will put a little green square around it, I suppose. So we did get here, and we can even make a guess. If I think the derivative of sine theta is going to be cos theta, I mean, it would kind of make sense for like this to be 0 and this to be 1. Uh, that would kind of make sense. So, but these are question marks at this point, and that should be a clearer question mark on that one. Like I'm kind of, if I'm matching things up, if I'm making educated guesses, if I'm saying how might this work out, this is all very gut feeling, this is not precise. We're just making a guess here. So let's go back and look at this a different way. One way to look at the derivative more fundamentally was to look at the definition of the derivative, the kind of algebraic structure. But the thing is that sine and cosine are really kind of geometric things. They're more naturally in the geometric world than in the algebraic world. So if we want to bring them into the algebraic world, it, can sometimes get a bit messy. So let's look at this more geometrically. Sorry, I keep moving my papers around over here. Let's look at this a little more geometrically. I'm going to try to keep my color coding like fairly reasonable here. We're going to look at a first quadrant. And we're looking at the unit circle here. So I have an angle theta, and then I have an angle delta theta. I would normally think of delta theta as being small, but I'm going to draw it big so that we can see things a little better. Delta theta. And we think of delta theta as being small. So I have a couple points on this curve. Let me maybe draw them in black. This point has, and this is the unit circle, so circle of radius 1. I think I said that, but didn't write it. This point, this bottom right point, has x coordinate cos theta and y coordinate sine theta. The other point, the one that's on the top left, well, the total angle from the positive x-axis going up to there is theta plus delta theta. So that has x coordinate cos theta plus delta theta and y coordinate sine of theta plus delta theta. Okay, so I'm starting to see my kind of, sine theta plus delta theta minus sine theta kind of popping up here. I can imagine drawing a horizontal line from my top left point over to where it ends just vertically above my bottom right point, and then coming down at a 90-degree angle. I see that change in height, I'll call delta y. And what is that? It is sine of theta plus delta theta. Oops, minus sine theta. No parentheses needed there. So that's what delta y is. All right, so I'm working my way towards something that looks like a derivative here. I would also like to know what is delta x. So delta x is going to be this, the length of this horizontal line here. Let me get a little more space down here. And if I have this pseudo triangle, it's not quite a triangle, pulled out here. I have my black curve as an arc. I have delta y, I have delta x. And what is the arc length of this arc? Well, let me draw this in blue. The arc length of a circular arc is r delta theta. But my radius is just 1, so this is just delta theta, this arc here. I could construct a triangle by connecting these 2 points with a straight line. So the two red sides in the green straight line do actually make a triangle. The two red sides and the black curve don't quite make a triangle. However, if delta theta is small, well, this arc doesn't deviate much from this green line. So the green line distance is approximately delta theta. So let me come in here and erase the black curve. So I have this approximate triangle here. This green delta theta is approximate, but in the limit as delta theta goes to 0, this approximation is going to get closer and closer and closer to being accurate. And in the limit, it will be accurate. Okay, so what else do I know? I know that the derivative of sine theta, well, from up here, from the definition of the derivative, the derivative of sine theta is delta y over delta theta. Taking the limit of that as delta theta goes to 0. So I've reinterpreted this geometrically, and now I kind of know what delta y and delta theta are geometrically. Okay, what else do I know? So let me come up here. I think I haven't used green on this picture yet, so I'll use green for this, even though I used green for the line down here. And I gave these names. Let me keep the names the same as in my notes. So I gave this the name P, this point here, this point the name Q, and this corner here I called R. So what color do I want to use now? I guess I'll just use black for this. So we know a couple things that I'm going to write off to the side here. I'm trying to keep all of this somewhat organized, but there's just a lot to write on here, and I'm trying to keep it color coded. But so we know that the arc length from P to Q is delta theta, and the green line from P to Q, where is green, has length approximately delta theta. What else do we know? We know that RP, that angle, is perpendicular to, here is the origin. Here is a point, point that I called A over here at 0, 1. Here is the origin O. So RP is perpendicular to OA. What else we have? The line PQ in the limit is the tangent line to um, the curve at P. Let me move this a little bit. I don't know how that. So with PQ being the tangent line to the curve at P, this tells us that PQ, that line is perpendicular to OP. So PQ, and so we have OP. Oh, let me draw that a little better. We have OP and PQ. So these meet at 90 degrees as well. And so basically what we can do is think of taking our red corner and rotating it. Which way would that be? Clockwise, 90 degrees, and lining it up with basically O to this point. Let's call this point B to P. So all of this to say that my blue theta here, I've made two similar triangles now with all of this geometry. My blue theta here, if I rotate my red triangle around, then I see it's going to be in the same corner down here. So what did I call this? This was corner R. So the angle RPQ is the same as the angle BOP. I think I have those in the right order as well. And this is in the limit. So this, and this are in the limit as delta theta goes to 0. But what is delta y over delta theta? At least in the limit when this, when I have a triangle instead of a curve, and instead of the hypotenuse being a curve, and when this length, instead of being approximately delta theta, is equal to delta theta. Well, relative to the angle theta, this is adjacent over hypotenuse. Cos theta gives me the adjacent over hypotenuse. Or this is in the limit as delta theta goes to 0. This is cos theta. So most of the hassle here is trying to keep straight what I want to call everything and um, and what's true about these two similar triangles. So I wish I had a couple more colors, but I kind of have, maybe I'll try to do this with a highlighter. I have like this side and that side, the yellow sides. I do have more colors in here, so maybe I'll try to do this. That side and that side. And then in the limit, when this turns into a straight line, that bit and this bit, this actually works a lot better with these highlighters. Those are my two similar triangles. And of course, we have a 90-degree angle here. So rotating around, we see that this angle theta has got to be there. right? Similar triangles have the same angles. So we see we've made two similar triangles, one kind of up on top of the curve and one next to the x-axis. So we were able to associate these two angles, the original angle theta that we started with at the very beginning of things, and this angle theta up here. And that's really where we came down here and said, okay, what is dy d theta, delta y over delta theta, geometrically speaking? And geometrically speaking, we see that that's cosine theta because cosine theta is the adjacent over the hypotenuse. And this is, again, and the limit is delta theta goes to 0. So this has to be cos theta from this geometric argument. Again, I mean, I don't think this is the prettiest argument. A lot of times these geometric arguments rely so much on naming everything carefully and keeping straight, like what's orthogonal to what and what's parallel to what and all of that. So they're sometimes not, I don't think anyway, the prettiest or most elegant arguments. But at least in my mind, this one is more intuitive to follow than just directly looking at these limits. But this was our geometric proof that the derivative of sine theta is cosine theta. Now, what can we get out of that? If we've proven the derivative of sine theta is cos theta, and that has to be true for all theta, well, there is a sine theta and there's a cos theta. The coefficient of sine theta must be 0, and the coefficient of cos theta must be 1. Right? This is going to turn out to be a number irrelevant of what theta is, as is this one. Right? Since these two limits, sine delta theta over delta theta and cos delta theta minus 1 over delta theta, those don't depend on theta at all. And this has to hold for all theta. My OneNote is being very laggy now. I think I drew too much on it with different colors and highlighters and all that. But these limits are going to be numbers. This relationship has to hold for all thetas. So it can't, if it just had to hold for one value of theta or something, then there's a lot of different solutions that could be possible here. But this has got to be cos theta for all thetas. So the coefficient of this sine theta has to be 0, and the coefficient of this cos theta has to be 1. So we get out of here corollaries. Oh, that should say 0. We get out of here two corollaries. Limit is delta theta goes to 0. Sine delta theta over delta theta is 1. And limit is delta theta goes to 0. If cos delta theta minus 1 over delta theta is 0. And by a similar argument that starts off the same way, we can show the derivative of cos theta, which would be the limit of cos theta plus delta theta minus cos theta over delta theta. We can break that cos theta plus delta theta apart using the cosine of the sum of two angles formula. And we'll end up with a limit that looks kind of similar to this one, where we'll have these same two limits in delta theta. And then we can use these two limits, and we can algebraically prove that the derivative of cosine theta is negative sine theta. So cosine's derivative is not sine theta, but negative sine theta. And that does make sense, right? If we look at cosine theta and we look at sine theta, I see, of course, the horizontal tangents of cos match with the zeros of sine. But I see that sine is positive from 0 to pi, where the tangents of cosine are negative, and sine is negative where the tangents of cosine are positive. So we do graphically see this sign difference here as well. We could go through and we can make a similar argument as up here, just looking at delta x over delta theta. We can make a similar argument and prove the statement geometrically as well. So at this point, we could basically use this setup and prove this geometrically, or we could use the fact that through that initial derivative of sine theta equals cosine theta, we got these two limits, and we can use those two limits to solve this algebraically now. Either way is fine, but I'll leave that as an exercise to show this. Personally, I like algebraic manipulation much more than geometry because I always feel like I'm trying to use, colors in a good way, and then I, either don't have enough colors or I haven't labeled enough things, or I label something a little bit differently than in my notes, and then I'm like, wait, what corresponds to what? And so I've never been a great geometer. I'm better at the algebraic side of things. Okay, so exercise, work through this proof. And as an example, let's compute the derivative of the tangent of theta. Now, again, I suppose we probably could go through a similar argument like this to discuss the tangent of theta and its derivative. And of course, all of our 6 trig functions have really an inherent relationship to that unit circle. Sine and cosine are the most obvious ones, but the others have relationships as well. But they're a little less common, a little less obvious. Let's approach this one geometric or algebraically instead of geometrically. Oh. The derivative of tan theta is the derivative of sine theta over cos theta. So by definition, that's what tangent is. And here I actually know the derivatives of both cos theta and of sine theta. And I just have the derivative of quotient. So what does my quotient rule say? Well, I divide by the square of the bottom. And I have bottom, derivative of top, minus top, derivative of bottom over bottom squared. The derivative of sine is cosine. So I have cos squared theta, cosine theta times cosine theta, minus sine theta times the derivative of cosine, but the derivative of cosine is negative sine theta. So that's plus sine squared theta over cos squared theta, or this is just 1 over cos squared theta. And we can choose to write that as secant squared theta. So derivative of tangent is secant squared. And as an exercise, compute the derivatives of the other 3 trig functions using a similar method. The derivative of cotangent theta is going to be similar to this one. For derivative of secant and cosecant theta, we can either use quotient rule, or when we get to the chain rule, we can make those, for instance, cosecant theta is 1 over sine theta, but that's just sine theta to the negative 1 power. I could use chain rule on that if you wanted a little extra chain rule practice. Or maybe, do one of them one way and one of them the other way for secant and cosecant. Any questions so far? Okay, so we have an example. For what values of x does the graph of y equals x plus 2 sine x have a horizontal tangent? So we want to know, when does f of x equals x plus 2 sine x when does f prime of x equal 0? Well, we can just differentiate f prime of x. The derivative of the sum is the sum of the derivatives. So that's 1 plus the derivative of 2 times sine of x. The 2 comes out front. And the derivative of sine of x is cos x. And I want to know, when is this 0? Now, this is something that we kind of often see in calculus problems, especially as we kind of move a little further on in the course, is, you're doing a problem in a Calc 1 course, you're answering, say, this question, and like we're basically done with the calculus at this point, right? We have maybe one step where we apply a calculus concept, and now we have an equation to solve, or now we have, some algebra to do, or something to simplify, or maybe setting up an equation from some geometric principles, or some like distance equals rate times time kind of thing. So it's quite often the case that, we do a lot of non-calculus to maybe set up the problem. We do maybe one step of calculus, and then we do a lot of non-calculus to simplify things or to finish off the solution. So for instance, we need to be able to solve this trig equation, 1 plus 2 cos x equals 0. Or this tells me cos x equals -1/2. So I know that cosine relates to the x value. So I should have a quadrant 2 and a quadrant 3 solution from 0 to 2 pi. Right, that's when the x is negative. And then what do? Well, I find my kind of, I think they call it a principal angle usually. I find this value of theta here, and then I subtract it from pi and add it to pi to get my two solutions. And then I add 2 pi k to both of those to get my my kind of symmetric solutions, my translationally symmetric solutions. But let's start off with asking, when is cos theta equal 1/2? So this is kind of our scratch work over here. Well, we know we have a special triangle. Oh, my OneNote's also like glitching out a little bit here. I have a 1, 2, √3 triangle. And I know that these angles, this is a 30, 60, 90 triangle. This is 30 degrees, or that's 1/6 of 180 degrees. That's pi over 6 radians. This bigger angle, 60 degrees, or pi over 3 radians. But I know that cosine is adjacent over hypotenuse. So if I want to figure out what angle gives me adjacent over hypotenuse of 1/2, that's this angle here, pi over 3. So pi over 3. So that's the angle that I want to put in here and here. So my answers are x equals pi minus pi over 3, and x equals pi plus pi over 3, and then plus 2k pi. Or if I simplify that down, I guess I used x in actually two places here. One is in the angle and one was on the xy axis. So call this one like x tilde or something. So I end up with two solutions. Pi minus pi over 3 is 2 pi over 3 plus 2k pi, or 4 pi over 3 plus 2k pi, where k is and integer. So these are all the values of x for which my graph of this function has a horizontal tangent. Any questions on this one? Give me 1 second here just to restart my OneNote. Sometimes when I have it open for a long time, especially if I use a bunch of different, I think it's when I use different colors that it starts to glitch out. Maybe it was the highlighters that did it, I don't know. All right. All right, there we go. Didn't want to zoom for a minute, but I think it's back up and running now. I should find a better program to use than OneNote, but it's so easy to use because it's just on all Microsoft machines and easy to port everything over. Okay. So now let's look at a couple other examples in this section. These are examples of limits. And we're going to leverage the fact that we learned about these limits through the process of computing the derivative of sine. So if we look at limit x goes to infinity of x times sine 1 over x, we might be kind of tempted to think that this just blows up. You know, doesn't the x head off to infinity and sine is like stuck between -1 and 1? You know, does this just blow up to infinity? Well, let's be a little bit careful though. Well, let's be a little bit careful though, because really this bit, this x is going to infinity. But sine 1 over x, well, that's going to sine of 1 over infinity or something like sine of 0. So that's something like 0. So I have kind of an infinity times 0. I have a number getting bigger multiplied by a number getting closer to 0. Well, this is an indeterminate form. This could end up being 0. It could end up being infinity. Could end up being something in between. I guess I could write this as something like sine 1 over x over 1 over x, like that, so that I have like sine of something over something, right? Just putting this x in the numerator as a 1 over x in the denominator, letting x go to infinity. That kind of actually has this form, the limit of sine of something over the same thing. But it doesn't quite work out super nicely because the limit of that form that I know something about is the limit as the argument goes to 0, not as it goes to infinity. But I do notice that as x goes to infinity, 1 over x goes to 0. Let me try to do this a slightly different way. I guess I can leave that there. Let me try to do this a slightly different way. Let me introduce a new variable. Maybe I'll call it t equals 1 over x. So then x equals 1 over t. So this limit would be the limit of what? Sine of t. And then x is 1 over t, so sine of t over t. So I've switched all my x's into t's. And then I need to ask, well, as x goes to infinity, what does t go to? As x goes to infinity, t actually goes to 0. We might want to say from above. That would be more accurate. And of course, limit t goes to 0 from above. Well, if I know that limit t goes to 0 in general, say sine t over t equals 1, then its right-hand limit is certainly 1. So actually, this limit equals 1. In other words, it kind of feels like sine of 1 over x is kind of acting like 1 over x near infinity. So like we just have x over x and they divide out and just give me 1 back. So it feels like near x equals infinity for large x, sine 1 over x just kind of acts like 1 over x. Or another way of thinking of it is it feels like near t equals 0, sine t just kind of acts like t. And this is actually one of the big things that we're going to see in calculus, this idea of linear approximations, super important idea, and it's related to this idea. And we could do a similar kind of approach here. We have limit x goes to 0 of sine of 3x times sine of 5x over x squared. And I kind of see that naturally I want one factor of x to go with each of these two factors of sine. And I break this into limit x goes to 0. Sine 3x over x times limit x goes to 0 sine 5x over x. And now what can I do? I suppose in the first limit, I know what limit sine x over x is as x goes to 0. Or I basically know what limit of, say, sine of 3x over 3x is as x goes to 0. That should also be 1. So if I had this, I would be good. I would know that this answer is 1. But I put in a 3 in the denominator. I need to multiply by 3 in the numerator. But of course, that can just come outside of the limit. And I didn't leave myself quite enough room there. And a similar thing with the second limit. If I have the same thing in the denominator as I have inside the sign, then that limit should be 1. If I really wanted to be formal, I could say, let t equals 5x, then I get limit of sine t over t. But of course, as 5x goes to 0, t is going to go to 0. As x goes to 0, 5x goes to 0, t goes to 0. And again, to put this 5 in the bottom, we need a 5 in the top to divide it out. So this is 3 times 5, or 15. So we can now solve limits that, look similar to, but not exactly the same as the ones that we originally investigated. But we do have to be careful to not, jump too quickly to conclusions. This limit doesn't turn out to be just 1. We do have to go through the process of, forcing it into the original form that we had and making sure that everything, that we get all of the details right, making sure that everything does work out just right. And these limits are 1, but we do have this extra factor of 3 and this extra factor of 5 that we have to take care of. Okay, any questions on this section? All right, so moving on to 3-4, the chain rule. And we might have enough time. We might be able to prove the special case of the chain rule today, or I might kick that to next time. But I want to make sure that we get through a couple of examples today. So some motivating examples for the chain rule. So consider the function big F of x equals parentheses x to the 4th plus 1 and parentheses all to the 6th power. Find f prime of x. Well, we could do this problem, right? We could multiply x to the 4th plus 1 by itself 6 times. OneNote loves making my 4s into 9s. And I could either maybe multiply this all the way out to what, a 24th degree polynomial. That's not going to be super nice to work with, but I could do it. Maybe I could leverage the kind of generalized product rule. Maybe I could do something like that. Oh, missed the 1 there. But I think we can agree that this isn't going to be super nice, right? Especially if I multiply everything out, get a 24th degree polynomial. differentiate all of my terms, and then try to somehow factor what will end up being a 23rd degree polynomial. That's not gonna work too nicely at all. Maybe using the generalized product rule, that might actually be reasonable to do here. You could give that a shot. And at a glance, I don't think it would be too terrible. I don't think it would be, actually, I don't think it would be that bad at all. But we're actually going to see that by applying the chain rule, it's going to make this possible but cumbersome problem actually almost trivially easy. Another example like this one here, g of x equals e to the x squared, or in other words, it's the exponential function e to the stuff with x squared plugged into it. So e to the power x squared. We want to find g of x for this function. These kind of functions come up all the time. For instance, the normal distribution in statistics, the bell curve. It looks more or less like e to the negative x squared. So these are important functions. This isn't just, some crazy function that will never actually come up. We want to find its derivative. And actually for this one, if I didn't have the chain rule, I wouldn't even know where to start really. This one up here, I might be able to find a couple of different approaches that might work. That might be kind of messy or might not be too terrible. But for this one, not even really sure where to start. Okay, so what does the chain rule say? The chain rule says that if I have a function that's the composition of two other functions, we've looked at how derivatives work with sums and differences of functions, works very nicely, just splits the sum or difference apart. We've looked at how derivatives work with products and quotients of functions now, so we understand how derivatives work with combinations of functions. But something like this is inherently a composition of functions. It's like a function, the exponential function, that has another function, x squared, plugged into it. And that's what the chain rule is all about. It's about compositions of functions. So if g is differentiable at x, and if f is differentiable at g of x, remember with a composition, the output of the inner function is what's getting plugged into the outer function. So that's why f has to be differentiable at the output of g. Then the composition is differentiable at x. So we have a statement that differentiability is available in this case. And we have a formula for it. We have a formula for the derivative of the composition of the functions. So if big F of x equals little f of little g of x, big F prime of x is little f prime evaluated at little g of x times little g prime of x. Note that this bullet here is a times, just to make it clear that these are being multiplied. This little open dot is composition, so that means f of g. And as a side note, if we use the this kind of ratio of differentials form, if we set u equals g of x and y equals big F of x, or little f of little g of x, or f of u, then we can say that d big F dx equals d big F du times du dx. And this actually has a very nice look to it, right? We're not technically multiplying and dividing by du and then splitting things apart, but this fractional this fraction looking notation looks like a fraction for a reason, because we are really taking the limit of the ratio of delta y to delta x. That's why we call it dy dx. So there is kind of inherently something that feels like a fraction going on here. And it's almost like I've multiplied and divided by du and then just kind of split it apart into two fractions. Now again, this is three pieces of notation that this thing is equal to this thing times this thing. So it's not strictly speaking that we're applying fraction algebra here and literally multiplying and dividing by du and splitting apart. But it certainly has that feel to it, and this notation, I think, really represents that feel. Okay, so let's apply it. Let's work through these three problems, and then if we have time at the end, we'll go through the proof. All right, let me copy this down. We'll just pop it over here, as well as this. So let's consider big F of x equals x to the fourth plus 1 all to the sixth power. So again, that initial problem we were looking at, we probably could solve this. We definitely could solve it with like sledgehammer brute force method, multiply everything out and differentiate. Super messy. We probably could make use of our generalized product rule to get a solution to this that probably wouldn't be too bad. It probably would look like what we're going to end up coming up with here. But you could imagine if the 6 was replaced by a 10, or maybe if it was even replaced by, say, a 1/2, that might not work so well. So what can I do here? Well, the first thing that I want to do, oh, I need one more piece. So the first thing that I want to do is I want to ask, this big F is the composition of which two functions? I want to, in some sense, kind of like decompose my big F into the composition of two functions. So I want to find a little f and a little g. I'm going to call the little g's variable x. I'm going to choose to call the little f's variable something different. It's not strictly necessary, but it gets confusing because, like, if you call this little f of x, then the x that's in the little f of x is not the same x that's in the little g of x or in the big F of x. So this x, this one, and this one, those are all the same x, but the independent variable for little f would not be representing the same thing. So that's why I'm choosing to call little f's variable just a different name. I'll choose t. Now I want to find a little f and a little g that satisfy basically two constraints. Number one, importantly, of course, their composition has to be big F. But like, there's a couple ways I could break this up. I could choose g of x to be like x to the fourth, or I guess I could even choose it to be like x squared, or like x to the fourth plus 1, or I suppose I could really even go crazy and choose g of x to be the whole thing, x to the fourth plus 1 to the sixth power, and then f of t would just be t. There's a lot of different ways I could break this up, right? Could I choose g of x just to be x, and then f of t is t to the fourth plus 1 to the sixth? Could I choose g of x to be like x to the fourth? And then f of t is like t plus 1 to the sixth. There's lots of different choices I can make. So what's my second constraint? I want to be able to compute f prime and g prime easily. I want to decompose my big F into two component functions, each of which is easy to differentiate. This is not easy to differentiate. This is not easy to differentiate. So there's usually kind of like a Goldilocks decomposition. How do you figure out what decomposition you want? Well, number one, you need to be pretty decent at composing functions together and recognizing compositions of functions so that you can, kind of pretty reasonably quickly go through what are different possible ways to decompose the function into two component functions. And you also have to be pretty quick at recognizing, okay, what kind of functions do I have derivative rules for that are going to be easily applied, and what kind of functions are going to be a little bit more of a pain to take the derivative of. So in this case, and as an aside, a lot of this comes with experience, right? The first couple of these you do, you're going to try, a half dozen different decompositions before maybe you land on the right one. And then, problems 5 through 10, you're going to maybe occasionally have to try 2 or 3 decompositions and sometimes hit it right the first time. And problems 10 to 15, you'll often hit it right the first time, sometimes have to try a second time, right? So with experience, you get a better feel for this. But if I can take this entire inside of the parentheses and make that g, x to the fourth plus 1, that's an easy function to differentiate. What would that leave me over? What would that leave me with for f? F of t would have to be t to the 6th. So that when I plug x to the 4th plus 1 into f of t, when I plug g of x into f of t to get f of g of x, I get x to the 4th plus 1 all to the 6th power. But t to the 6th is also easy to differentiate, just the power function. So there's lots of ways that I could choose a g of x and an f of t that would compose to make big F. But this is kind of like the Goldilocks, right? I'm not putting so much stuff into g that g is hard to differentiate. And I'm not putting so little stuff into g that what's left over in F is hard to differentiate. I can kind of balance that complexity. G is a little bit complex, F is a little bit complex, but each of them are fairly easy to differentiate though. Okay, so now let's look at this kind of prime notation over here. What do we mean by this? What is f prime of g of x? What I mean by this is find d by dt of f of t and evaluate that at t equals g of x. So figure out what the function f's derivative is in terms of t, and then plug g of x into the derivative of f. So in other words, f prime of t is 6x to the 5th. Basic power rule. I bring the power down in front, take 1 off the power. So big F prime of x is little f prime. Oh, not an x there. That should be a t. So big F prime of x is little f prime, which is 6 times something to the 5th power. What is that something? I want it to be g of x, the original g of x, x to the 4th plus 1. And then what do I multiply by? Well, simply g prime of x. So I have 4x cubed. Again, bring the power down, take 1 off the power, and then the derivative of the plus 1 term is 0. And maybe I could simplify this to like 24x cubed, x to the 4th plus 1 to the 5th power. So that is my chain rule. I've worked my way through one problem in the chain rule. Now, again, as you get more used to this, there are some shortcuts you can take. You'll get more used to how to break up, how to decompose the function into component functions that kind of satisfy that criterion that both of the resulting functions are easy to differentiate. But it just takes some time. It takes some practice and getting used to it and just seeing a lot of problems so you get that pattern recognition under your belt. Now, there are some problems like this one that are pretty straightforward. We have a function e to the power x squared, which, especially if I write it this way, the exponential function evaluated at x squared, well, it's kind of obvious what the functions ought to be. So I want to find little f of t and little g of x. So the big G of x equals little f of little g of x. So little f is kind of the outside function and little g is the inside function. My outside function, it looks like, is uh, the exponential function evaluated at t, or just e to the t. And my inside function, g of x, is going to be x squared. It's what's getting plugged into the exponential function. And then what's my derivative then of big G? It's going to involve little f prime and little g prime. Maybe I'll just compute those over here. Little f prime of t is e to the t. It's the same as little f of t. And what is little g prime of x? Just 2x. So what is big G prime of x? Well, I take f prime of g of x. So e to the power g of x. And then I multiply by g prime of x by 2x. Or I might write this as 2x e to the x squared. Any questions so far? Okay, another approach that I could take is something like this. I could say, if I have the derivative of the square root of x squared minus 4, if I let u be x squared minus 4, my OneNote is going really slow. Sorry, it's kind of messing with my writing and having to undo a bunch of things. So if I pick u equals x squared minus 4, if I give that a different name, u, then really what I want to do is compute the derivative of the square root of u with respect to x, though. Or I want to compute d by dx of u to the 1/2 power. Now, if this was d by dx of x to the 1/2 power, I could do that super easily. But d by dx of u to the 1/2 power, my variables don't match, so I can't just use the power rule here. But what can I do? Well, what I can't even select things now. I don't know what's with my OneNote. Sometimes, some days it works great and some days not so great. Um, but up here, I can change the variable I'm differentiating with respect to. Instead of d by dx of this thing, I can choose to differentiate with respect to u of u to the 1/2. But then what do I need to do? I need to multiply by the derivative of u with respect to x. So what's d by du of u to the 1/2? Well, I bring the power down and I subtract 1 off the power. And then what's du by dx? What is the derivative of this function with respect to x? Just 2x. Or this ends up with, well, the 2 over 2 goes away. I end up with x over square root of u. But remember, u was a variable that I chose to introduce. It's nowhere in the original problem. I should get rid of the u's. I should switch the u's back into x's. And that's my derivative. So I think when you're starting out, it's easier to use this prime notation formula. Once you get a little comfortable with how things decompose, it's, I think, a little quicker to use a strategy like this, where you kind of write out, all the steps, and you write out the change in the variable that you're differentiating with respect to, keeping in mind that when you change that variable, instead of d by dx, you have d by du. You need to multiply by a du dx at the end to adjust for that. And at some point, 3 weeks or a month or something from now, after you've done a bunch of chain rule problems, it's almost going to be second nature. You will typically not have to even write out anything. You'll just be able to look at this and say, okay, this is basically a power function. It's something to the sixth. I differentiate it like a power function, sixth stuff to the fifth. But then I got to remember to multiply by the derivative of the stuff inside, 4x cubed. And it'll really just be that quick that you'll go through, and it's almost like you're figuring it out at the speed that you're writing it at when you get used to it. But that takes some time. That takes a lot of practice. That takes doing, 50 or 100 problems and seeing a lot of the patterns over and over again and knowing what they look like more intuitively. So it's not always, in probably almost every problem from here on out in the course, the chain rule will make an appearance. But it's not always like this cumbersome to compute the derivative. It is the first few times that you do it. It gets a little better when you can transition to a thought process like this one down here. And as you, do more and more, the ability to decompose in the right way initially, to look ahead and see what derivatives you're going to need to take and how things are going to fit together, gets faster and faster over time. So again, take a look at that chain rule practice worksheet, work through that over the weekend, not to be handed in for for a grade or anything like that, but we'll review that in the next class meeting. We'll work through it. Take some of the other examples that I did, like the this one and this one, yeah, the h of x one. Take these two, maybe apply the chain rule to this. This is stuff to the -1 power. Can we decompose that and use chain rule, get the same answer, right? You can get a little more practice that way. And then when we come in next time, we'll start with that practice worksheet. We'll also do the proof of the chain rule, a special case of it, and move on from there. Do a couple more problems in the chain rule and continue on with chapter 3. So that is that's the plan for next time.